So first of all, what is a force? So the definition of a force. A force is a vector defined by three elements. The first one, I would say they are all important, but the most important one is the magnitude. Then the second one is the direction. And the third one is the point of application. So we generally define a vector with a force, with an arrow like this. F is the vector. And the symbol is with an arrow at the top of the letter, which can be F or P, for example, or Q or any other letter. Generally, it's a capital letter. Of course, in reality, forces cannot be seen. You cannot see a force, but you can see the effect of the force itself. For example, if I press my smartphone on the table with my muscles, my arm, I'm applying a force on the smartphone. I don't see the force itself, but if I have a microscope, then I can see the stress distribution on this surface, between this surface and the table itself. So I press the smartphone and there will be like a compressive stress distribution at the interface. So I can see the effect of the force. So these three elements, magnitude, direction, and point of application, are mandatory in the sense that we cannot define a force without these three aspects. Of course, as any other vector, we can make operations between vectors. Which can be addition, subtraction, generally also the product between vectors. The simplest force type is the weight of a book, for example. So if I take this is a small, let's say, book, its weight is 200 grams. So generally, we see that the self weight of a book, for example, this one, is generally applied in the centroid, the center of mass. We will see how to get this point, which is generally called G. And W is the self-weight of the book itself. So this is a force. This is a special kind of force, which is called the gravitational force, or gravitational load. This is an example of vector, of force vector, because it has its magnitude, which can be, for example, W 100 grams, or if we take a vocabulary, for example, it will be 1 kilogram, or if we take, I don't know, 1 cubic meter of concrete, it will be 22 tons. So we can have different magnitudes for different types of elements. So each element in nature and then also the structures, have their own weight. And the first general concept that you should learn is that all the buildings must be able to absorb any applied load and the self-weight, their self-weight. So each structure will have a certain amount of loads, of forces applied on it, and it must be able to absorb them without fail. Clear? Okay, so generally we need a Cartesian representation of forces. So for example, if I have a force in space, let's assume that the coordinate system is this one. In space, of course, we have 3 axes, X, Y, and Z. So each force can be represented by a vector, as I said. And we'll have 3 components. So the 3 components are the components of each axis. So we'll have to project into the 3 planes the force itself. So we'll have, for example, the force here in XY plane, which can be decomposed into with parallel lines. So this line is parallel to the x-axis. Okay. So I repeat it. First, you have the force vector, F, which is in a 3-dimensional space. Do you hear me from home? Yes? Okay. Okay. So you have basically this force vector, which has its projection into the XY plane, which is this first element here, the projection into the XY plane. Then you have to draw this line. I will draw it again to show you, okay? So first point is this one. Then you take the line parallel to the x-axis, which is this one. So this line will be parallel to the x-axis. And your x component will be this one of the force itself. So this will be Fx. It will be a vector, so we have to add an arrow as well. And the same we do for the y-axis. So we take the parallel starting from the intersection point. So from this point, we draw the parallel axis. And we take the y, sorry, I've written x, it's y, of course. And we take the x component, which is a vector as well. Okay, x, of course, x is on the x-axis and y is on the y-axis. And finally, the vertical component. The vertical component is perpendicular to the vertical axis. So we take again this projection and we'll have this vertical vector. So these are 3 vectors. So basically, your generic force F is given by the sum of the vectors Fx plus Fy plus Fz. all three vectors. Is that clear? It's just a decomposition. This is called the decomposition of a vector. So you can decompose any vector into three components. The three components are generally the components of the coordinate system, x, y, and z. That is simple. Okay. Then, when you want to calculate the magnitude of your vector, generally you use this notation. You use these two vertical signs. This means the magnitude of the vector itself. Magnitude, the intensity, okay? Which is given by a sort of Pythagoras theorem. Let's say it's not a Pythagoras theorem. It's like a algebraic decomposition, which is the magnitude of the first component, exponential 2, plus the magnitude of the other component, exponential 2 as well. And we make the same for the third component under a square root. So in this way, we find the magnitude of a vector. Let's make a numerical example on a plane. So we have a plane. Let's assume that we are considering plane x, y. And we have a force vector which has an angle with respect to the x-axis of 45 degrees. So this is the force. And I know that f x, which is the horizontal component of the vector. I also know that fy is the vertical component of the vector. These are vectors as well. Okay, these are vectors. I know that f is the resultant vector because this is the sum of the vectors. So I can write that f is equal to fx plus fy. This is the addition between vectors. If I want to, so let's assume that fx, so this is given, okay? This is given that the magnitude of fx is equal to the magnitude of fy, and it is equal to 2 kilonewtons. So first important thing, the unit of a force is a Newton, decanewton, kilonewton, meganewton. This is like something that you must know for sure. So you cannot tell me that the force is measured in meters or... Yeah, you laugh, but there are a lot of you who says that at the exam. So a force is in kilonewton or newton or decanewton or whatever. Okay, so 2 kilonewtons, they have the same force. So if we want to express them in terms of coordinates, we can say that fx is as points 2, 0. Because 1, 2, and 0 because the y component is 0, right? And fy as the x component 0 and the y component 2. So these two equations are the same as what is written here, because it's written that the magnitude of the two forces is 2 kilonewtons, right? Yeah, of course. So fx, if you want to, I mean, let's assume you have a vector, okay? You forget the force for now. You have two axes, x and y. You have a point here, P. What are the coordinates of this point? If this is 1, 3, and 0. Okay. If I take this point, P1, what are the coordinates? 2 and 3. 1, 2, 3. Okay? So the force is the same because the tail of the force finishes at point here, it finishes at point 2, 0. Okay? The other force, Fy, finishes at point 0, 2. Clear? Yeah. It's not an answer. This is given by me. Now the answer, we have to get it. Okay? Just a moment, we will get it. Okay? So now we take this expression. Okay? And we want to find the magnitude of f, which is the sum of the two vectors. So f, we take this, and f, the magnitude, is square root of fx times exponential 2, sorry, plus fy exponential 2. So, okay. Is that clear? So I have that the magnitude of this, the first one is 2 exponential 2 because the magnitude of the first horizontal force is 2. The length of the intensity is 2. And the other one is 2 as well. So it will be square root of 4 plus 4.
Is it referring to this?
Yes, this was just an example, not regarding, okay? This was just to explain why 2, 0 and 0, 2, okay? So now we have under square root, we have 8, which is, you can take out of the square root what? 4, exactly. 2 square root of 2, okay? So it's nice because you can solve these problems. Thank you, Parsa, for the answer also. Yeah, you can answer also in chat. It's nice. I appreciate that. And I was saying that in these problems, you can find a solution by different ways. For example, in this way, which is called analytical approach. Analytical because you apply like the formula, which is the square root of the squares of the components, okay? But you can also, interestingly, you use other approaches giving the same result, which is the geometrical approach. So if I take the same case as before, and I have the two components, so I have fx and with the arrow, and fy with the arrow again, I can find the resultant vector with a simple geometrical consideration. Because if you look at this is a square of edge equal to 2. So the magnitude of the force is the diagonal of the square. And as you know, the diagonal of the square is nothing else than square root of 2 times what? The side, the edge, L. This is for a square. If you have a square which has edge L, then the diagonal is square root of 2 times L. Yeah. Yes, yes, you can. Yes. But this is simpler. Okay. Yeah, you can do that. We'll see how to do that. So now we are just looking at the main concept. So we'll have square root of 2. You see the results is absolutely the same, and it must be like this. It must be the same. So the geometrical and the analytical approach should deliver the same result. Otherwise, there is something wrong. So you should check why maybe one or the other is wrong, and you have to find out what is wrong and what is right. But it is a good proof, especially when you are not so familiar at the beginning with the vectors. You make both checks to see if it's correct or not. Okay, now let's introduce another couple of definitions. What are rigid bodies? Rigid bodies are bodies that do not deform. So if, for example, this circle is a rigid body, this is a sphere, for example. Okay? And I apply a load on that, for example, a force like this, which, by the way, it is called a concentrated force. So its unit is that of a force, so kilonewton, Newton. So with F, you indicate that is the unit of a force in general. Then when you have to express a specific unit, you can say kilonewton or decanewton or, I don't know, whatever, newtons and so on. So if you have a rigid body, since the body does not deform, you can translate the force vector without, of course, changing its magnitude and changing its orientation, so along the same line. That's important. So along the same line of action, you can translate the force in any other point of the rigid body itself, and it doesn't change. So this kind of situation is called that the force is a sliding force. So the force can slide without changing its effect on the rigid body. Because if I, for example, if I take my smartphone and if I apply a force here, for example, I apply, I don't know, ½ kilo here. Or if I apply this force here by pulling this one by 1 kilo, it doesn't change. It will move by the same quantity, okay? Because it's a rigid body, it doesn't deform. But if I take, for example, a very soft material, like cotton, for example, then things change because first of all, I talk about deformable. Oh, sorry. Yes, thank you. Deformable bodies. And deformable bodies deform. So this is the main aspect. So if this is a piece of cotton, for example, and I apply the same force as before in one point, and it will modify like this, maybe it will deform like this. In the application point, it will deform maybe like this. So in the violet, you see the deformed shape. And then if you take the same element with the same force, but the force which is, so the same line of action, but applied to another point, it will deform in a different way, like this, for example. Okay? So in this case, so it's very different. So only in rigid bodies we can translate the forces without changing the effect. Maybe displaced in English. You can displace a force by keeping the same line of action, the same magnitude and line of action, without changing the effect on the body. Okay? So there is a big difference between rigid bodies and deformable bodies. So anytime you have to ask yourself what is if the body is rigid, I will do something, or if the body is deformable, I will do something else. Are there any questions? Okay, let's proceed then. Now we see the types of forces. We have different types of forces. So the first one is concentrated force. This force doesn't exist in nature. So it's an idealization. Because I cannot apply a force into a very small point. It's not possible. There is always, like, if I use my finger, for example, there is always a surface, a contact there, even a small, even very, very small, but there is always like a contact surface, always. So the concentrated force is applied on a point. Because it applies on a single point with the area equal to 0. But in nature, it is not possible. So it is an idealization. The concentrated forces, we have said, is like a generic vector. F. Unit, force, or kilonewton, for example. Okay. Then we have volume forces. Which exist in nature. These forces are forces distributed over the volume of a body or of a part of it. An example, the most, I would say, famous example for volume forces, it's the self-weight. Because if you have a body, for example, you can take again a book. Big book. It will have a specific weight. So if I take each small cube, infinitesimal small cube of this book, each infinitesimal cube will have like a volume called dV, which is an infinitesimal part of the volume of the book itself. Then if I define gamma, gamma is something I would say fundamental in structural engineering. So gamma is the specific weight of something, specific weight of the material. So please fix this concept from now. And its unit is a force over a cubic length. So over a volume, because a volume has a cubic dimension, right? Do you agree? Okay. So an example of unit for the specific weight can be kilonewtons over cubic meters, for example. So if this book has a specific weight, I don't know what can be, for example, gamma 10 kilonewtons over cubic meters, okay? And we want to find W, which is the magnitude of the self-weight of the book. So what is the weight of the book? What is the muscle force that I have to apply in order to raise the book? And it can be a question. So I have to make an integral over the volume of the book itself. And it will be gamma, which in principle is different. So it depends on the point, because the book can have a specific weight higher in the corners. In the central part, it can be different. It's not constant always. It can be different. Times dv, which is the small part. So if we make the integral all over the volume, we get the self-weight. So if gamma is constant, so it doesn't change, for all the book is the same. So if you make a picture of all, if you would be able, suppose you are able to take a small cube from the book and you weight it to see what's the weight, so you can get the specific weight. And it will be different for many parts. But let's assume that it's the same for all the book. Then it's constant. So we can put it out of the integral sign. Okay, so we can say that it is gamma integral in the volume of dv. But integral in the volume of dv is simply the volume of the book. So volume. Is that clear? So generally, even for building materials, the specific weight is the same for all the parts of the material, just not to complicate it. So generally, you can say that a self-weight of something is the product of specific weight times volume. Is fixed. Okay. How to compute the volume? I really hope that you know how to compute the volume. In any case, I express it. So this is L, for example. This is L first. And this is the thickness. So these are the 3 dimensions of the book itself. Okay. What's the volume of this? Make a guess also, online students. Write down in the chat what is the volume of this book. Yes, Rahaf is right. So in class here, nobody knows what is the volume of the book. Also Mireza, yes? Yes, is the product of the 3 dimensions, okay? So W is, let me write it in black. So V is L times L first times T, the thickness. For example, if L is 20 centimeters, or 30, times L first is 0.2, and the thickness is, I don't know, 5 centimeters, 0.05, we can compute with the calculator what is the volume of this book. 0.3 times 0.2 times 0.05, which is 0.003 in cubic meters. okay? And it's the same, of course, if I express everything in centimeters, I can say 30 times 20 times 5, which is, tell me, without using the calculator. It will be the measure in cubic meters times, make a guess, 10 exponential yeah, 0.003, 3000 exact, because we have to multiply by 10 exponential 6 because it's meter square, cubic, exponential 3 times 2. 2 times 3 is 6. So it will be 3000. So this is an equivalence. It means that, so this is math, basic math, guys, okay? So I won't explain that because in high school is explained also, maybe in the middle school is explained, okay? So if you have some doubts in it, just check it how to make equivalence. It's very important how to change this. Okay, so for example, if the specific weight we said it's 10 kilonewtons over cubic meters, then the magnitude of the self-weight vector will be gamma times volume, and therefore 10 times what we have to use, 0.03 cubic meters or 3000. Exactly, because we don't have to mix different units. So we'll use this. And what is the result? 0.3. Yes, I forgot one. Yes, sorry. The result is 0.03. Perfect. Okay. So in kilograms, because 1 kilogram force is 1 decanewton. So your weight probably will be 50 kilograms or 50 decanewtons or 60. For the men, up to 80 maybe. Okay. So 0.03 in kilograms is, or in decanewton is, how much? How many decanewtons are 0.03 kilonewtons? That guys. Excuse me, you have kilonewtons. Then attonewtons, decanewtons, newtons, and so on. So 1 Newton is, 1 kilonewton is 10 hectanewtons. 1 decanewton is, 1 kilonewton is 100 decanewtons, and 1 Newton is 1000 newtons. Okay? So 0.03 kilonewtons. How many decanewtons are? 3. Okay. Is it possible that a book weighs 3 kilograms force? Yes. If it's heavy, yes. Yeah. Yes. International system of units. Yes. Not feet, not just newtons. Yeah. Newtons, meters, yes. Okay. So Yeah, anytime we make an operation, we have to ask ourselves if it's correct or not. If it was like, I don't know, 30 decanewtons for the book, maybe there was something wrong, okay? So I have always to see if my result is realistic. This is the most important thing. Okay, so the result is realistic because 3 decanewtons is good for a book. So probably since the volume is correct for sure, then the specific weight is also correct. Okay, and now the last example of, then we take a break. The last example, so we said volume forces, we said concentrated forces, volume forces, and the third type of force is area or surface force. So it is a force which is applied over a surface. So it implies the presence of a surface. So it implies also that there are at least 2 bodies in contact. So for example, if with my hand I press on the desk, I'm very bad in drawing, but let's assume this is the desk. So if I press my hand, what happens? I'm applying like a force. In principle, it's kind of concentrated force. But then I have to know what is the area. So the area is the surface of my hand. That will be some tenths of centimeters square, maybe, I don't know, 10 15 maybe centimeters square. So the area is this area of the hand. If F is the concentrated force I'm applying to the desk, on the desk, then I have a compression stress, which is generally defined as a sigma. This is the Greek letter sigma, which is equal to F, so the magnitude of F, the force, divided by what? The area of the hand, exactly. So as you can see, I need to know what is the area before writing the surface force or the area force, because otherwise I cannot express the area force, right? Okay, in your opinion, now I have a question for you. So in buildings, from your intuition, no need to know anything about buildings, what is an example of area force or surface force? Sorry? Column? Column is a structure. Yeah, it's a structural element, column. Yes, we can say that the column is applying like a surface area on the bottom of the column itself. Yes, in this case, yes. Sorry? Furnitures, yes. Also they are, yes, yes. People, yeah. Sorry? Foundation, yes. And if you have to think about some climatic action, snow, yes. Snow is a very typical surface or area load. Indeed, if you have, for example, a roof, the roof is maybe inclined because we are on the mountains. And the snow is very important for structure. So we can, we have a load exactly on a surface. So we have to compute it. So Q snow is a typical example of surface or area force. Also wind, because we can have wind also as a horizontal action on the structure itself, also involving all the external surface of the building itself. Sorry? Wind, yes. Rain, no, because rain actually like goes away. Yes, in this case, yes. If you have like a pool or something which can contains rain, yes. For example, you have like yeah, a pool, or the English term is like serbatoio in Italiano. I don't remember now the English. A tank, like a tank on a roof, for example, like this. You have many times tanks. And if they are filled with water or other material, yes, this is but actually, this is not actually an area surface. What is this water inside? Volume. So water in this case acts as a volume force, not like an area force. You can say the same for the snow, but for snow, for water, you can actually measure the height of water, but for snow, no. So snow, you don't go there and measure. It's very aleatory, probabilistic, you know. So for snow, generally, there are standards which tell us, okay, you take, for example, in the Alps, you take 2 kilonewtons over square meters, for example. So in this case, for snow, it's an area. But meaning that snow is a volume of something, also it can be intended as a volume force. Okay, so this is the main difference. Yeah, please. What about? Sorry. Yes, also from the other side, if the wind goes from right to left, is still some action that you have to consider. Yes, it's also a surface load. Did I reply to your answer? I mean, it's irrelevant because you can also have, you have to consider also the wind from the other side, yes. Inside the building? This one? Ah, yeah, the depression. Yes. Yes, it is, especially for special structures which have specific shape. For example, tall structures, you have to consider also the depression force given by wind. This one, right? Yeah. Yes, yes. You can have it also a suction force is called, because it comes from the wall to the external part. So this is like a distributed load. So you can consider it in one sense, one orientation, or the opposite one. But these remain area forces, okay? Or if you have a dam, for example, you have a dam which is filled by water. So the water level is maybe this one, H. And this can be represented as an area force. The horizontal force acting on the dam. This can be represented as an area force, or as a volume force, as we have said. For water, the answer is always both. Okay. Good. Do you have some questions? Or let's take a break now. Yeah. Last question. Sigma, yes. It's the Greek letter. It's generally used for stresses, pressures. Okay, and it's small letter. Okay. Yeah. Yeah, they will be very much used. Seismic waves, yes. Seismic waves, Magdalena, yes, of course. Also, it's an horizontal action, but seismic waves is something that it will be different. It's a ground displacement. So it will have an effect. It's not a directly applied force. And wind, snow and foundation, roof, furniture and people, perfect. Marzi, Raf, Magdalena, Armin, all parts, all of you. Raf, very good. So what is a free body diagram? It's an example. Let's see it as an example. So you have, if you have a rigid beam, where are the others? Can you call the others, please? Someone can go out and call the others. Oh, thank you. Yes, they are coming. Okay. Now, because we have said 15 minutes and 50 minutes. Okay. We don't wait your friends because, I mean, 18 minutes passed and we have to start also for you who are present. So for yourself, basically. So the free body diagram, we make an example. Let's take a beam, either deformable or rigid is the same, with two supports. We will see what are supports in the next classes. So far, we take this beam with two supports, which can be like, normal supports, you know. And we have like a central load acting on this beam. We call it P, central force. The free body diagram, since these supports exert reaction forces, the first thing I have to do to solve a mechanical problem is to use the free body diagram. So I need to change this given mechanical scheme into a free body diagram. So I take the same beam as before. I put the force in the middle as it was before, and I substitute the supports with the reaction forces. The reaction forces are V1, V2, H1, and H2. So basically what I did, I substituted the supports or any other part of the structure to get the free body diagram. So I've obtained the free body, which is basically the beam plus all the original forces and the reaction forces. Okay? So this is the definition of free body diagram. And the definition of internal forces is when I apply a cut into the beam. For example, in this position, I make a cut. So through the cut, I can zoom in this cut. It will be like this, for example. I cut in a specific point of the beam itself. It's a generic cut, of course. It's not, it mustn't be like in a specific position, but in any position. And the forces in the interface of the cut, will have two interfaces, will be called internal forces. So generally they are expressed as in triangular shape like this. So we have two triangles like this. Sorry, this is the opposite. So like this. It's not important now to draw perfectly these internal forces. It's a general distribution of internal forces. So these are the internal forces or stresses. They are a measure of the internal stresses of the stresses in the material. Okay? Is that clear? So I can make in any point of this, now that you are all arrived, please, when I say 15 minutes, come in 15 minutes. Otherwise, I have to start. Okay, so please next time will be, please be on time. Okay, so I can apply any cut in any point of my beam. Of course, this beam, in this beam, it remains the load P, it remains the same as it was before. Let me draw it with the same pen, like this. I can make any cut in any place of the beam, and through particular machines or now answer your question in chat and say it just a moment. So I practice a cut, and from this cut I know that making any cut there is a distribution of internal stresses. Why these stresses are important? Because I need to know what are the stresses into the material in order to be sure that this stress is less than the strength. Otherwise, my material fails. So structural engineering, do you remember the title of the book, which I suggested before? It was like, why buildings fall down? Because the failure of buildings is, I I mean, the thing that drives more a structural engineers. A structural engineer. So he or she wants to avoid in any way the failure of the material itself. So it's very important to know the internal stresses into the material itself. Do you see the screen at home? Now it's blocked. I mean, now I'm moving it, but it's fixed. Okay, thank you. So yeah, just okay. So the question is, why does it have to look like that? Why isn't there more force the more we go up, since there is the external force? I don't actually understand very good your question. I mean, very well your question, but I suppose that you are referring to the stress distribution that you see here. This is, we will see what will be the real stress distribution. It depends on the Navier's formula. So if the material is homogeneous, for example, this value of stress is equal to this value. Always, this is always valid. But in the Navier's formula, this value sigma, we call it sigma plus, is equal to sigma minus on the top. We will see it. It's from the Navier's formula. Okay? Say yed. Okay? No, I'm asking your friend here who asked that question. If you want to make another question, you can switch on your audio. Okay. Okay, so these are just two definitions and the important aspects, because we will use a lot the free body diagram, and we will also make a lot of cuts into the beams to understand what is the internal distribution. So we need to understand the difference between them. Then for forces, it is valid for forces, it is valid this law that probably you know, which is, I write it in Latin, actio is equal to reactio. I read it in Latin, in Italian, let's say. It's like, do you know this force? Yeah, what's its name? Yes? Newton, the third Newton's law, exactly. So it's the third Newton's law. So it's the most important law. My professor of physics usually told us that you will understand all the physics if you really understand this formula. So you can imagine, we were like 19 years old and he told us like this. You already know the physics if you understand this formula. So, and initially we didn't understand, and we started to understand that inside the formula there can be like a very wide knowledge. Okay, good. Now let's see how can we compute the sum of concurrent forces. So we can have, first of all, what are concurrent forces? Are forces with a given magnitude. It must not be the same magnitude at all. One can be 1 Newton, the other one 2 kilonewtons, the other one 3, etc. They must have one point in common. So their line of actions, I just write the definition. Their lines of action intersect at one point. Okay? So for example, we have this F1 or P1, F2, and F3. These are three concurrent forces because their line of action intersects as one point, in one point. Of course, also another example can be, for example, this one, F1. F2. And F3. So the forces can be also separated. The important thing is that their line of action, so if you make an extension of the action line of the forces, must intersect at one point. So these three are concurrent forces. You can have a generic number of concurrent forces in general equal to n. It's not mandatory that you have a specific number of forces. And these forces are generally applied to a body. So let's take, for example, a rigid body, this red shape. It's like a normal rigid body in which these forces apply. What we want to find, bless you, is the resultant force. The resultant force of these three. So there is a method, very nice, very simple, that you can use always. It is called head-to-tail method, or addition head-to-tail. You can, for this method, it is important to say that you can start from any vector. You don't have necessarily to start from F1, okay? You can start from F3. The important thing is if you start from a vector, then you follow like for example, the clockwise direction and you take all the vectors. For example, if you start from F2, you take first F2, then you take F3, and then you take F1. So like this. Or if you start from F1, then you take first F1, then F2, then F3, okay? So you just follow this order, or in counterclockwise direction is the same, it's irrelevant. For example, let's start from F2. So we take first F2, we put F2 in here. Then we have, then it's called head to tail. So we have to take the head of F3, sorry, the tail of F3, which is the last point. So this is F2. So we attach to the head of F2 the tail of F3, and we have this. These are not actually the same. Let me see if I'm able to be parallel. Yes, like this, maybe better. This is F3, okay. And then I have F1. So F1 is something like this, around like this. So you have to attach the head to the tail of the three vectors. So it's a drawing, it's a graphical method, it's simple. Then what is the resultant? The resultant, look, it's very simple. The resultant is this vector. You have to take the tail of the first vector and the head of the last vector, and you connect these 2 points, and the resultant is this one. So the arrow must be in the direction of the head of the last vector, okay? So this is the resultant. So for example, we will see, probably not today, because today is maybe late. So tomorrow, if you bring with you your laptop with AutoCAD installed, It's nice because we can say how to use AutoCAD to compute vectors, which is much faster than use the analytical solution. So this is the addition head to tail. So you can say that, taking back, recalling the previous expression, that R is equal to F1 plus F2 plus F3. So you can say that. Okay? And interestingly, this is a very important definition. This is called force polygon. So what is a force polygon? Is a polygon containing the force vectors assigned, given. Connecting the forces, connecting the vectors. Okay? Now I give you an exercise that you can solve for tomorrow. And we will solve it, let's see, either tomorrow or next Tuesday, because I want to check if you are too tired. Maybe we solve the exercise in that occasion because you are tired. Otherwise, I have to see either tomorrow or next week. But I give you the exercise because it's quite important to understand what we have said today. So if you make this exercise properly, it means that you have understood what we have said today. Another thing, next week, in Wednesday probably, so bring your computer. All the time it's better to bring your laptop, even if you don't use it. You don't have it? No problem. Yes, you can. That's up to you. Yeah, it's not mandatory, but it's something useful if you have it. It's good to have it. Otherwise, no problem. But when you will have to, next week, we'll make a simulation of the midterm already next week, because I want to make a lot of simulations, a lot of exercises. So I will prepare some questions about the things that we see in the lectures, and you will have to answer. So no grade at all, no, don't worry, but it will be made in the Moodle platform. So you'll have to be able to access in the Moodle platform, because we will make these questions, these tests very often to test your preparation. So you can understand if your preparation is good or not, okay? If you have to study more or not. So the exercise is this one. By the way, this is an exercise that you find in the book of Gross, Engineering Mechanics, Statics. So, yeah. Yes, for example, this one will be in the portfolio. Yes. Yeah, all the exercises that I assign must be in the portfolio. And also others exercise, also the exercises done in class. For example, the one that we made, this one, for example. Yes, it must be done. It must be reported in the even if it's very small, one row, but it must be reported, okay? So we have an eye bolt, round one, which is subjected to multiple forces. So these forces are Let me check. I don't want to make, okay. F1. F2. F3. They are not to scale. And F4. So if F is the force, the generic force, the inclination angle with respect to the horizontal axis is alpha. Okay? So the numbers are, the magnitude of the forces are F1, F2, F3, F4, you have 12 kilonewtons, 8 kilonewtons, 18 kilonewtons, and 4 kilonewtons. I repeat, they are not to scale in the drawing. I tried to keep the scale, I mean the angles, but not the scale for the magnitudes. So the corresponding angles are alpha 1, 45 degrees, alpha 2, 100 degrees, alpha 3, alpha 4. Alpha 3 is 205 degrees, 270 degrees. Just as an example, F3 is this one. And the angle is alpha 3, this, okay? So you should find here the reaction force, sorry, the resultant force. The reaction force will be later. The resultant force R and its inclination angle with respect to the horizontal axis. So X is this horizontal axis. Okay. Hint, you can proceed either analytically, so applying the sine and cosine functions. So you just, first of all, you use a coordinate system, X and Y, and you will find for each force the horizontal component and the vertical component. And then you will use sine and cosine functions. This is the one option, or you can use the graphical solution by hand or with AutoCAD, for example. I suggest you to make both just as a check. Because if you have the same result, then you are sure that it's the correct answer. I mean, it's the correct procedure. Do you have some questions here or? Yeah, please. Which point you need to edit in our portfolio?
Is it like, for example, our notebook, we can just scan it and put it there, or it could be a separate layout where we need to write it down? Like, at which point?
No, it must be separate from the notes. So it's in the way that you copy the exercise in another part. Yes, only exercises. No, 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 no exercises. And why are you doing like that? For example, in this case, if you apply the graphical aspect, you have to write. Now I write, for example, the force polygon, and yeah, the method is the head to tail method, like this, and you show and you describe step by step. Okay, good. So for now we have finished. Thank you. See you tomorrow. Bye.